Hello everyone, my name is Lukáš Hrpa and it's my pleasure to give a talk about planning in zero-sum games. So this is a joint work with my colleagues Pavel Rytíř and Rostya Horčík. So in real-world environments it might be the case that there are some other agents with conflicting goals, so such that they are competing for customers or for resources. So this means that generated plans should be optimized for strategies of these other adversary agents. So to do so, we can leverage game theoretic methods such as the well-known double oracle algorithms, so that can generate randomized strategy for the agent. So, and in our previous work, so we combined automated planning with double oracle. So the problem is that the plane combination didn't really scale well. So in this talk, so that I will be talking about heuristic methods that improve the scalability. So I believe I don't really have to introduce planning, so that here we consider durative actions, those that are defined in PDDL 2.1. We consider action costs and soft goals, so which means that these goals don't have to be achieved, but for each of the soft goals which has not been achieved, so there is some penalty given to the agent. So in zero-sum games, so that whatever agent gains, the competitor loses, and vice versa. So the thing is, in our case, if an agent achieves a soft goal, so the competitor can no longer achieve the same soft goal, and of course vice versa. So, and also the reward for achieving a given soft goal is the same for both the agent and the competitor. So to give you an example, we define a resource hunting domain where there are two teams of UAVs, so the blue one and the red one, that there are competing for these resources, the green ones. So to make it slightly more challenging, so that the resources can be collected by specific sensors that the UAVs can carry. So that, for instance, here this UAV with sensor 3 can collect these resources. So some resources require two sensors to be collected, which sometimes can be done by a single UAV, but sometimes so that there have to be two UAVs that have to collect the resource. And once a resource is collected, so the resource is gone. Now we will leverage the well-known double oracle algorithm, so one of the best known algorithms in game theory. So that the double oracle is based on solving restricted games, so that the restricted game has, let's say, several strategies, or several, in our case, several plans, so for each of the agent, and by solving the restricted game we are assigning optimal probabilities for executing each of the plan. So when we do this, so we try to compute a best response, or any response which improves the result, which improves the player strategy. So, and if we can, so that we just add that strategy or that plan into the restricted game, so then we try to compute best response for the other player, and we iterate until we are no longer able to improve the result. So, to give a planning perspective, so that we have what we call critical facts. So that critical fact is present in the initial state. It is required by some agent actions, but that fact can be deleted by some competitors' actions, and however it cannot be achieved by agent's action. So for instance, so that the availability of the resource is a critical fact, so that so it is required by the collect actions, but the competitor can collect it before and delete the fact which can no longer be re-achieved. So, and the actions, the agent's action required in critical fact are called critical actions, and similarly competitor actions deleting a critical fact are called adversary actions. So the main idea is to plan agent's critical actions before the adversary action. So in other words, application times of adversary actions are setting deadlines for agent's critical actions. So, and since we know competitors' randomized strategies from Double Oracle, which are in form of a set of plans, each with a given probability for execution, so that we can determine the cost of agents' critical actions. So, such that for those situations, so we are missing a given deadline which is set by a given plan, so with a given probability, so we will be penalized for failing to achieve a given soft goal, so that which is, for instance, the value m, right? And of course this is the sum across all the planners, across all the plans. Also we are considering the tie situations in which we are planning our critical actions at the same time as the adversary ones, and in such a case, so we have a 50% chance to succeed. So, just starting with our heuristic approaches, that one is motivated by the well-known Hmax heuristic, so, and we leverage that concept to develop an algorithm that estimates earliest action application time. So that this is really similar to Hmax, so that we have for initial facts we have time equals 0. So, and for action, so we are just maximizing across the time of the facts in action precondition. So here we relax the at end precondition, so because otherwise it will be much more complicated, yet it will not compromise the property of the estimation that actually is let's say lower bound of the actual application or earliest possible application time. And for fact, so that we just choose the minimum of the times of the facts achieved by action effects. So this algorithm can help us with pruning those critical actions whose earliest application time is after all the deadlines. So therefore such a critical action has no chance to succeed, and hence we can prune it out. So another technique actually selects and gives some partial order to critical action, so that the planner doesn't really have to decide which critical action and in which order they should be applied. So therefore the planner is just filling the gaps in between. So for that, so we just adapt the previous algorithm by considering some actions with fixed application time, and we also considered some effects of these actions, so that we know that certain facts will be true at some time, and so on. So the details are given in the paper. So here we are considering so-called clusters of critical actions, where each cluster corresponds to a particular soft goal. So in other words, these clusters are in fact disjunctive action landmarks for a given soft goal. So, and what we do iteratively, we are selecting critical actions from not yet considered cluster. The time of the critical action is not estimated to be after the latest deadline, and with, let's say, all the possibilities in a given step, it yields a minimum cost of the plan. So, and the cost is estimated from the time estimates or the application time estimates of critical actions. So, and we simply continue until we can select these actions. So, and at the end, we just ordered selected actions that are, let's say, dependent on each other. So, for instance, actions that are using the same UAV, so they can't really be executed in parallel. So now to improve our selection and ordering techniques, so we leverage simulated annealing. And we considered two types of operation. So one is changing order of critical actions. So for those critical actions that actually have defined the ordering constraint, or we can substitute a different critical action for the action from the same cluster. So, and the objective function is to minimize the estimated cost of the plan, which is estimated by the same way as before. Now, so we encoded the resource hunting domain as type strips, so that the details are given in the paper, so that we actually encoded time as like timestamp objects. And we considered two types of scenarios, so that we called middle and diagonal simply as resources are placed. So we use an optimal planner, which uses a potential heuristics, and a satisficing planner, the well-known llama planner. So, and for, let's say, each planning episode, each computational best response, the timeout is half an hour. So that for the optimal planner, so the results are actually the optimal values for the classical approach, which is just the plain combination of planning and double oracle, so that we can see that player 1 has slight advantage, so that it can collect in average slightly more than player 2. So with the pruning heuristics, so that the optimality is not compromised, because we are just pruning critical actions that are useless. So of course the optimality is compromised with the using of ordering heuristic or the local search approach, even though the optimal planner is used. But what you can see for the local search approach, actually the values are quite close to the optimal ones. And so if we go to the results where we use satisficing planner, so we can see that we can scale beyond 3 UAVs up to 8. And if we just look at the results of the local search, so that even though we were not really able to compute the equilibrium, so as a rule of thumb, so that since these scenarios are let's say proportionally scaled, so therefore if the values of player 1 and player 2 are close to each other, so that we believe that they are close to equilibrium. So that this is what you can see in most of the values for the local search. But I mean, sometimes there are huge discrepancies, and this is the most profound example, so where the player 1 collected all the resources, right? And I mean, the reason for that is not just that the heuristic doesn't give a perfect estimate, but also sometimes when the satisficing planner is used, that the plans are not of the best quality. So, and in this case it simply was a poor quality plan for player 2, which somehow couldn't be improved, which simply led to this result. So, I mean, in summary, so the good news that our heuristic works and scale beyond the classical approach, because it really doesn't scale beyond 3 UAVs, so at least we could do for 8. And with local search heuristics, so the results are of reasonable quality. So just to mention, so you can see in the paper that the runtimes are in order of thousands of seconds, just to just compute the, let's say, whole game. And it depends on the number of double oracle iterations, and also what I would say, complexity of planning tasks. So, I mean, typically the planning tasks are quite hard for the planner, so if really we need to calculate, generate plans that are close to optimum. So, and as I said, so sometimes these strange results are caused by generation of very suboptimal plans. Thank you for your attention.